Hi everyone, thanks for coming. I'm going to talk about optimal advertising for information products. This is a joint work with my advisor Yiling Chen. Internet has provided easy access to a large amount of online data. As a result, there's a new type of product that's being traded more and more commonly in our life. And unlike traditional commodities, these products provide us with certain kind of information that help us make better decisions. For example, there are all kinds of online newspapers that tell us what's going on in the world, and there are a lot of apps that give us information or advice about all kinds of things like traveling or driving or dining. Other examples include ranking, like ranking of colleges, or datasets and database access. So for this type of information product, it has been long observed that freely revealing some partial information may increase the seller's revenue. For example, movies have trailers, and online newspapers usually provide free beginning paragraphs or pages. And dataset platforms allow the buyers to browse the dataset or even give free random sample of the data. But this should not be the case if we follow the commonly used assumption in models of asymmetric information that all the agents share a common prior. But the plausibility of assuming common priors is questionable. So in this work, we do not assume common priors exist, but consider the more general setting that individuals' beliefs are the primitives of the model. And the individuals will perform basic updates based on their own beliefs. We show that in this more general setting, partial information disclosure can lead to higher expected revenue for the seller. And we also study the optimal strategy for a long-term information seller. So let's start with the model. So we have some information buyers who care about an unobservable payoff relevant state, denoted by omega. For example, it can be an unknown flight delay. And these information buyers face a decision problem. So they need to choose an action A from a set big A, and their utility depends on both the action that he takes and this unobservable state. And each of the buyers holds a personal belief about state, denoted by a distribution theta. We have a long-term information seller who can always fully observe the omega after it's realized. And the seller wants to sell this information of omega to the buyers. And the seller can use a strategy to review some partial information before selling the information. So we formally define a seller's strategy as follows. A seller can use an advertising rule that consists of a set of signals that the seller can send to the buyer, and a signal scheme that specifies how the signal should be sent, and also a price menu that defines how to set the price. And when using an advertising rule, after observing omega, the seller will send a signal with probability pi omega s specified by the signal scheme. And when s is sent, the seller will charge a price ps for the full revelation of omega. So let's look at an example. Suppose there's a flight tracker who wants to sell the information of some flight delays. And she can first review the range of the exact delay. For example, she can first tell the buyers whether the delay is below 2 hours, or between 2 and 5 hours, or longer than 5 hours. And then the seller can charge different prices for the revelation of the exact delay. And for a buyer with a personal belief, for example, the delay is distributed uniformly between 0 and 10, he will update his personal belief after observing the signal sent by the seller. For example, the delay is higher than 5 hours, then the buyer's personal belief then becomes the uniform distribution between 5 and 10. So the timing is as follows. We consider a long-term information seller who posts an advertising rule at the beginning. So this can represent that the designer first decided a strategy that she's going to reveal some random sample of the data set that she's going to sell in the future, or she decides that she's going to reveal the range of flight delays. And then on day T, a new state will be realized. And the buyer arrives, who holds a personal belief about the state. The seller fully observes the state, and then she sends a signal using the posted rule, and then charge a price for the full revelation of omega. The buyer observed the signal sent by the seller, and he updated his belief by performing some Bayesian updates, and then decide whether to purchase the exact omega at price PS. So the seller's goal is to choose a mechanism that will maximize his expected revenue. We assume that the seller knows the distribution of omega and theta, and she can choose the mechanism based on the distribution. So in this work, we mostly focus on the case when the seller targets buyers with a specific type. So this can happen when the majority of the buyers share a common belief. For example, they follow the same Twitter account, or they read the same newspaper. We consider this case to be a good first step to understand the information seller strategy, and we're able to characterize the optimal mechanism for the seller in this case. So the first question one may ask is, can partial information disclosure really increase the expected revenue? The answer is yes. So let's look at an example. Consider a binary state with omega equal to 0 with probability a half, and there's a buyer who tries to guess this state. And the buyer holds a biased personal belief that omega equal to 0 with probability 3/4. Then we can plot the buyer's valuation of knowing omega as a function of his belief, which reaches the highest point 0.5 at belief 0.5. If the seller revealed no partial information and just directly sell omega, then her revenue cannot exceed 1/4, which is just the buyer's valuation at belief 3/4. But consider a seller using the following strategy: that the seller sent S1 with probability 1/3 when she observed 0, and sent S2 with probability 2/3. And when seller observed 1, she just sent S1. Then when signal S1 is sent, the buyer will have a belief 0.5, meaning that he will be willing to pay 0.5 after observing S1. Then the seller's expected revenue will become 1/3 because signal S1 is sent with probability 2/3. So what we observed in this example is actually not a coincidence. We showed that solving the optimal mechanism is actually equivalent to finding the concave closure of a function f at point theta. So this is an example of a possible f and its concave closure. The concave closure of a function is basically the minimum concave function that is above that function. And this function f is defined on all possible beliefs about omega. And the value of this function at point theta is equal to the expected revenue without any partial information disclosure, and the value of its concave closure is equal to the optimal expected revenue when the seller can reveal some partial information. And the optimal mechanism is defined by the points of contact between these two functions. So this function f is a function defined on all possible beliefs. It's the product of two components. The first component is what we call the likelihood ratio. So it basically represents how much the buyer's belief theta deviates from the marginal distribution of omega based on a belief eta. So it's defined as the expected ratio between mu omega and theta omega based on belief eta. And the second component is what we call the cost of uncertainty. It represents how much the buyer is willing to pay for knowing omega when his belief is eta. So it's the difference between the buyer's expected utility knowing omega and without knowing omega. So this function f, which is the product of these two components, is not concave in general. This means that its concave closure will be different from the function itself. This means that partial information disclosure can be beneficial in general. But in the special case, when this target type is equal to the marginal distribution of omega, this function will be a concave function. Then in this case, directly selling the information without partial information disclosure will already be optimal. So now we know that finding the optimal mechanism is basically finding the concave closure of a function that's a product of two components. But computing this concave closure may not be easy. So we give an important observation that will help us solve the optimal mechanism. This observation is about a type theta buyer's posterior after observing the signal sent by the seller when the seller uses an optimal mechanism. So this will reduce the possible location of a type buyer's posteriors to a relatively small space. Then we only need to focus on the mechanisms that will push the buyer's belief to that relatively small space. To give the observation, we need to define a set of points that we call confusion points. So define set PA to be the set of beliefs about omega based on which action A is the best action to take in expectation. And we define confusion points to be the vertices of these PAs. For example, let's consider a state omega with 3 possible realizations, and the buyer has 3 possible actions. Then if we plot all possible beliefs about omega as a triangle, we can divide this triangle into 3 different regions in which each of the action is the best action to take based on the beliefs in that region. And the confusion points are just the extreme points of these regions, which are marked in red in this plot. We can see that the confusion point consists of the point at which the buyer is indifferent between 2 of the actions or all 3 actions, as well as the degenerate distribution at which the seller or the buyer knows the exact realization of the state. And let eta S to be the posterior of a type theta buyer after observing signal S. Then our observation says that there exists an optimal advertising rule that always have posterior eta S lie on the segments between the confusion points. So based on this observation, we are able to formulate an exponential size convex program that will solve the optimal mechanism. And this convex program will have a polynomial size if the size of omega is a constant, or the size of the action set A is a constant. So one may wonder that whether we can do better than this because we still have exponential size convex program. So we prove that it may not be possible to find a polynomial time algorithm because the problem is NP hard. Besides this convex program, this observation also has an interesting implication. So when the buyer faces a decision problem that only has a few options, we can show that there exists an optimal mechanism that tells the buyer a lot about state. So formally, we can prove that there exists an optimal advertising rule which allows the buyer to reduce the range of omega to a relatively small set. And the size of this set is no more than the number of options times 2. So this means that if we look at the buyer's posterior after observing the signal sent by the seller, it will only be non-zero at a few positions, the number of which is bounded by 2 times the number of actions. So this is due to a property of the confusion points. We can show that a confusion point will not have a lot of non-zero entries, so the number of which is bounded by the number of actions. And combine this with the fact that there exists an optimal advertising rule that always have the bias posterior lying on the segments between conversion points, we can get this result. Finally, we'll briefly mention our result for the general problem. So for the general problem, where the bias type is drawn from a distribution and the seller knows that distribution, it is NP hard to find a constant factor approximation for the optimal advertising rule. But when it is not too hard to predict the possible types of the buyers who will make the purchase, it is possible to find an epsilon suboptimal mechanism using a linear program. To summarize, in this work, we study the optimal partial information disclosure strategy for an information seller. And we mainly focus on the case when the seller targets buyers with a specific type. And in this case, we'll characterize the optimal mechanism using a concave closure representation, and we'll make some important observations about the optimal mechanism, based on which we formulate the finite size convex program that will solve the mechanism. And for the general problem, we prove it's NP hard to have a constant approximation, but we give an approximation algorithm for a special case using an LP. Thanks. I'm happy to take any questions.